So take a quick second and ask yourself, are you in motion right now? Even if you're sitting perfectly still on the couch or at your desk, the truth is you are moving. The Earth is spinning on its axis. We're all literally hurtling through space orbiting the sun. Motion is just absolutely everywhere. It's in the fluttering of a butterfly, the falling of a leaf, and of course, the cars zipping past your window. And because motion is just so universal, we really need a solid framework to, well, actually understand it, measure it, and predict it.
Welcome to This Explainer. Today, we're diving headfirst into the core concepts of kinematics. Now, that's just the branch of physics that deals with motion. We're going to build our understanding from the ground up, taking those everyday actions you see all around you and translating them into the totally fascinating language of predictive physics. Okay, here's our roadmap for today. First up, position, distance, and displacement. Then, speed versus velocity. Third, understanding acceleration. Fourth, visualizing motion with graphs. 5, the kinematic equations. And finally, uniform circular motion. Let's get into it. Section 1, position, distance, and displacement. So before we can even begin to talk about how fast things are moving, we absolutely have to talk about where they are, right? To measure any movement at all, we first need to agree on an origin, or what physicists call a reference point. Imagine trying to give someone directions without a starting point. It's impossible. The reference point is that fixed anchor we start counting from. It completely dictates everything else we observe about an object's position. Now, here's where it gets interesting. There's a crucial difference between two words we usually use interchangeably in everyday life, distance and displacement. But in physics, they are very different beasts. Distance is simply the total path you covered. It doesn't really care where you went, just how much ground you crossed. Displacement, on the other hand, is the shortest, straight-line path between your starting point and your ending point. And suddenly, boom, direction matters immensely. Think about a runner on a track or a swimmer doing laps in a pool. This is such a great way to picture it. If that swimmer powers through a 50-meter lap, swimming 25 meters to the other end and 25 meters straight back to the wall where they started, their total distance traveled is 50 meters. But their displacement? It's exactly 0. Crazy, right? Because they finished exactly at the reference point. If you only care about where they ended up relative to where they started, well, it's as if they never moved at all. Section 2, speed versus velocity. All right, bringing time into the mix allows us to calculate how fast all this displacement is actually happening. Just like distance and displacement, speed and velocity are kind of like a dynamic duo, where one is simple and the other, well, it tells a much deeper story. Speed is just the rate of distance covered over time. It's the number on your car's speedometer. It just tells you how fast you're going. But velocity? Velocity gives us the whole picture by taking that speed and adding a specific direction to it. Because it's based on displacement, knowing a car is going 60 kilometers per hour is speed, but knowing it's going 60 kilometers per hour due north, that is velocity. Moving right along to Section 3, understanding acceleration. Okay, let's be real. In the actual world, objects rarely maintain a constant, perfect velocity, do they? They speed up, they slow down, they turn, and that brings us to acceleration. Let's define this super clearly, because acceleration is simply the measurement of how quickly velocity is changing over time. It's not just about how fast something is currently going. Actually, you can be moving incredibly fast, but have 0 acceleration if your speed and direction aren't changing at all. Now, this is one of the most fascinating concepts. When you press the gas pedal in a car, you speed up, right? Your velocity increases and you're accelerating in the direction of your movement. But here's the wild part. Hitting the brakes is also a form of acceleration. You're changing your velocity just in the opposite direction. Your velocity is going forward, but your acceleration is acting backward, which is exactly what causes you to slow down. We measure this in everyday terms all the time, especially when we talk about cars. Look at it this way. If car A can go from 0 to 100 kilometers per hour in just 5 seconds, it has a really high magnitude of average acceleration. It changed its velocity super quickly. But car B, it takes 10 seconds to make that exact same change in velocity, so its acceleration is much lower. Make sense? Section 4, visualizing motion with graphs. So let's dive into how physicists actually visually track these changes. Obviously, we don't want to get lost in a sea of numbers, and graphing motion is how we see the whole story at a glance. Comparing these graphs really opens your eyes. On the left, a position time graph with a straight diagonal line tells us the object is moving at a constant velocity. It's covering the exact same amount of ground every single second. But look at the graph on the right.
The second you see a curved line on a position time graph or an angled line on a velocity time graph, it immediately tells our eyes that the velocity is changing. And that means acceleration is happening right there on the page. And here's a really clever math trick hidden inside these graphs. If you have a velocity time graph, you can find the slope, the steepness of the line, and that actually gives you the exact acceleration. But wait, it gets better. If you calculate the shaded area underneath that line on the graph, that area literally gives you the total displacement. The visual shape holds the mathematical answer. How cool is that? Section 5, the kinematic equations. All right, this is the absolute climax of straight-line motion. We're going to take everything we've learned so far, from our definitions to our visual graphs, and turn them into predictive math. Now, don't get intimidated. Just think of kinematic equations conversationally. These equations act like a magic key, linking together initial velocity, time, acceleration, and displacement to predict future motion. If you know just a few of these details about an object's motion, these equations allow you to instantly predict where that object will be or how fast it'll be going at any point in the future. So, the absolute most crucial takeaway here is that these aren't just abstract textbook formulas. No way. These exact kinematic equations are what automotive engineers use every single day to calculate safe braking distances. They factor in the car's initial velocity, the negative acceleration of the brakes, and the driver's reaction time to actually engineer the collision avoidance systems in modern cars. This physics is literally saving lives on the highway. Finally, Section 6, uniform circular motion. Okay, let's throw a curveball. Literally. We've been talking entirely about straight lines so far. Let's step off that straight path and see what happens when objects move in circles. Here's a totally mind-bending concept for you. Think about a kid sitting on a moving merry-go-round or even a satellite orbiting the Earth. Even if they're moving at a perfectly steady, constant speed, physics says they are constantly accelerating. Wait, why? Well, remember, velocity includes direction. Since they're moving in a circle, their direction is continuously changing at every single fraction of a second. If direction changes, velocity changes. And if velocity changes, you've got acceleration. You can actually test this yourself with just a simple marble moving inside a ring of adhesive tape. As long as the ring is there, the marble moves in uniform circular motion. But the instant you lift that ring, removing the force that's keeping it in a circle, the object's velocity immediately carries it off in a perfectly straight line, right from that exact point. In geometry and physics, we call that straight line a tangent. The marble desperately wants to go straight. It's just the constant change of direction that forces it into a circle. And wow, that brings us to the end of our journey. We've taken apart the whole machinery of motion today, right? From the simple difference between distance and displacement to the math of kinematic equations, and finally into the surprising acceleration of circular paths. These invisible laws of physics govern absolutely every single move you make and everything moving around you. So I'm going to leave you with this. Knowing how velocity and acceleration actually shape reality, how will you see the motion of the world differently today? Look around, because the physics is absolutely everywhere. Thanks for joining me on this explainer, and hey, keep learning.